I hope this is recording. I'm just checking for the sound. Yeah, it's got sound. Okay. Today is gadgets, waves, food, and I bet we're not going to get to Tide. But first, we had a question from the last class. The question was, how do sodium lamps work? So we talked about the question was specifically about high pressure sodium lamps, but let's talk about them because there's two kinds. There's the low pressure and the high pressure, and there's sodium vapor. It's in a gas discharge lamp, so it's of that type. Now the low pressure ones, they're very efficient, but the light is yellow. These are both low pressure lamps, so the light that comes out is almost monochromatic, and it's in the yellow. It's good enough for street lighting, or at least people used to think it was. When you first turn it on, before you turn it on, the sodium's actually in solid form. And then when you turn it on, it heats up. There's some neon and argon in there, and it heats up, and then the sodium starts to vaporize. So it'll glow pink until it vaporizes, and then it'll turn yellow once that happens. Okay, so it emits pure yellow at 589 nanometers. Remember efficacy versus efficiency. So efficacy means how much of the energy do you put in, does it convert to light that you can see. So efficacy is related to your human perception. We see really well at yellow, so this is very efficacious, even though it's actually awful light because it's monochromatic. So let's look at the human eye response. And oh, look at this. I googled images, eye response, and here's all these eye responses. And notice how some of them peak at yellow, and other ones, they look like they peak at green. Basically, this tells me you can't believe anything you read on the internet. So, I did this. Here's the actual curve. Here's 589 right here, yellow. So it's actually past the... Remember I told you that we see best at green? Well, I have a PhD. I know what I'm talking about. Here's green, here's yellow. So I guess we can't believe everything we see online, but it is close to the peak, which makes them efficacious. High pressure sodium, the sodium, when it's cold, is present in an amalgam with mercury. And then when current flows through the thing, it gets liquidized. It's unstable, interestingly. So it's unstable. Current increases. As the current increases, it warms up, which decreases the resistance. So as it decreases resistance, the current increases, warms up some more. It's an unstable state. Remember positive feedback from some previous lecture. Boom! So then it will light up. When it gets hot enough, it becomes stable again. But the question is this the nature of your question? Why are these white? Were you the one who asked me the question, Farzad?
No, I think
it was Peter?
Yeah.
Was that the nature of your question? Why are the high pressure ones white and the low pressure ones yellow?
I think mine was just why is it efficient?
Ah, okay.
My question was why do they go out after a while? I'm not even sure if there are sodium pressure lights in the street, the ones that go out.
I don't think they are anymore.
Yeah,
if they were, you'd see them being distinctly yellow. Well, unless of course they're the high pressure ones.
Yeah, they're not yellow. They're kind of whitish.
Yeah. So the question is, why is this white and not yellow? Because it's still sodium that's emitting the light, and sodium emits at 589. We just said that. And the answer is something called pressure broadening. So for you engineering types, if you want to learn more about pressure broadening, you can take my laser class in the autumn. But basically, there's a high pressure in there, so that has the effect of broadening the spectrum of the light. What's happening is the sodium atoms are crashing into each other much more frequently under high pressure, and what that does is it shortens excited state lifetime for only engineers have to worry about this. And if you remember the uncertainty principle, the uncertainty in the energy times the uncertainty in the lifetime has to be greater than or equal than h bar. So if the lifetime gets shortened, the energy range gets spread, and that's pressure broadening. So whoever wanted to know why is it white. So here's the spectrum of the low pressure, boink, yellow. Here's the high pressure. It's got significant yellow, but it's got some other colors in there too. All right, so let's talk about gadgets. We didn't talk about gadgets last time, did we? Okay, it feels like forever ago since we were here. So things like vampire phone chargers. So we say that they consume power even when they're not charging anything. And people will sometimes say, well, why is that? If nothing's hooked up to this, no current can flow. But the answer is, here's what's inside this thing, circuitry. In particular, there's a transformer here. So again, for engineering types, transformer, the current will always flow through this transformer, even if nothing's connected to the output. And then there's some other circuitry in here that we don't have to bother to explain, but current can flow around in this stuff. So even when you're not actually charging your phone, if you're charging your phone, you'd be plugging it across this output. Even when current's not flowing through this, it's flowing through the rest. It's not a lot. Okay, 0.01 kilowatt hours per day. So sure, unplug it, but we need to do more than just that to solve our problems. Here's some other vampires from the book. Computers and peripherals, the computer box. This is interesting. On and active, 80 watts. On but inactive. Why would the computer be consuming power when it's inactive?
RAM usually.
It could be RAM, it could be stuff like keeping a clock and the channel memory energies, like in your TV, for example. Standby, even in your TV. Well, your LCD display when it's off, I don't know, there's TV on here. Oh, these are the different parts. So this is the CPU, this is the, nobody uses cathode ray displays anymore. A liquid crystal display, projector, laser printer, on but inactive, so it has to keep warmed up. Wireless and so forth, and your TV, you know, it's remembering all those channels. So even when they're off, some of those things are consuming power. Is it a lot of power? No, but it's there. LCD screens use astonishing little power because we have courses you can take, but they do have to be backlit. So liquid crystals in general, that's why we use them in watches and calculators, because they take so little power, it's not even funny. But for a computer screen, you have to be backlit, and that does take power. Remember we talked about those cold cathode fluorescent tubes that go in the back. So here is a plot of power usage in watts versus screen size in inches. Here's a plasma display. This says CRT screen. Who cares? Here's a DVD, VCR, LCD screen. Way down there, very little power. So they're still better than a CRT. Plasma power displays use a lot of power. Don't buy those. How can you tell if you have a liquid crystal? We talked about this the other day. Get out those polarizers, or if you don't have any, get out your polarized sunglasses and rotate that in front of your screen, and you'll be able to see. Clocks, music, TV. Here's some more objects. A portable CD player, 2 watts. Clock radio, 1.1 watts maybe. Here's another one, a little bit higher. Digital radio, 9. Radio cassette, stereo amplifier, different ones. Home cinema sound, DVD player 2, 12 watt. TV! Oh, that's because it has to emit all that light. Video recorder, digital TV, set-top box, clock on a microwave oven. And again, some of these consume power even when you're not actively using them. Other electronics, an Xbox. What is an Xbox? Is that a game?
Gaming system.
Gaming system. Oh, I stand corrected. I bet you these are too. Answering machines. Oh, who has those? Cordless telephone. Who has phones anymore? Does anyone here keep phones in your house? I'm like the only one left in America, probably. Vacuum cleaner. Here, this is your excuse not to vacuum very often. Takes a lot of power. Why is that? Big motor pushing a lot of air. Takes a lot of energy to do that. So McKay's estimates 5 kilowatt hours per day per person. I don't know if Americans use more than that or not. I think that England probably uses a lot of gadgets just like we do. How much effort would it take? So if you think about it, if you're trying to power this 2.5 watt 20 LED light for 40 hours, you'd have to pedal for an hour on this bike. Is he moving?
Pictures of changing.
Oh, bizarre. I wonder how I did that. I'm all powerful. I have no idea. Ultra efficient fridge, you'd only have to pedal that for 1 hour to run it for a day. Battery charger, compact fluorescent bulb, so you can get an idea here of how much work you'd have to do. Or if you prefer to do push-ups to run these things, you can do that. Not really. So, here's a poll. The U.S. uses 4 trillion kilowatt hours per year of electricity. How many kilowatt hours per day per person is that? How many people think it's around 4? Nobody. How many people think it's around 40? Maybe. How many people think it's around 400? We got a couple. How many people think it's about 4,000 kilowatt hours per day per person? This is how much electricity we use. It's actually about 40 per person, roughly. But remember, we use a lot of other energy, too. So that's electricity. Only 40% of U.S. energy used in a year is electric. So, for example, someone has to bring my groceries to the store. They're doing that in a truck that's not electric. All right, so here's where we are so far. These are the UK estimates. We still see that travel and heating dominate. Light and gadgets is not that significant. Even though that's what we think about, oh, I'm going to turn off that stuff when I leave. It's really insignificant compared to all this junk. Lights and gadgets, not significant. This tells us basically where we should cut back first. I think it's pretty obvious. All right, let's take a look at wave power. Wave power. So this is waves, energy due to waves, not tides. So people putting bobbers out in the ocean or in a lake or something, and as they move up and down, they generate energy. It turns out that wind causes waves, and the waves cause motion, and the motion can be converted to electricity. The amount of motion is greater near the surface than deeper down. So there's a number of devices out there. We'll talk about a few of them. You can generate the electricity out in the ocean. So maybe you have a magnet moving inside a coil, like that flashlight I brought in, only on a bigger scale. And as waves goes up and down, it generates electricity. And then you have underwater electric cables that go to shore and you distribute from there. Or maybe the moving bobbers somehow manage a pump, operate a pump, and it pumps water to shore, and then you use that water to drive a turbine on shore. So then you don't have the worry of transmitting electricity under the ocean. I have to take time out and tell you a story. So I'm a fiber optics guy, right? And there's this great story about the first submarine fiber optic link. So fiber optics, you have a laser at one end and you have a detector at the other end, and you modulate the laser and pulse it on and off, and you should send data across this fiber optic link. The first submarine link was between France and England under the English Channel. So the engineers that hooked this thing up to the transmitter, they got the fiber. It's on these giant spools, huge things, and they got this big ship, and they're going across the English Channel, and they're paying out the fiber, and they're paying out the fiber now. And then in a fiber optic link, as the light goes down the fiber, it loses energy, and eventually you have to boost it. So there's an amplifier there. So this is just light in a piece of glass. There's no electricity involved. But at some point you have to put in a repeater, which has a detector, and it takes the light, converts it to electricity, runs it through an amplifier, cleans it up, and drives another laser, and then sends the light on again. So you have glass, and then you have this repeater that's got some electricity in it, and glass, and then so they drop the repeater, they drop more cable, drop a repeater, drop more cable, hook it up to the receiver on the other side of the channel, and they hooked everything up, and they turned it on, and everything worked great, and the engineers are doing their happy dance, and we're all excited, and then it failed the next day. And the engineers are going, oh, please let it not be at the bottom of the ocean, because that's very expensive to troubleshoot. Let's hope it's the transmitter. So they checked the transmitter on shore. Nope, that was fine. Then they checked the receiver at the other side. That was fine too. So, oh darn, so they had to go and pull up all that cable. So they rented the big ship and they pull up all the cable, and the cable looks fine, the cable looks fine. They get to a repeater, and the repeater is all mangled and dented and squished. They're going, what happened? Well, it turns out light in glass fiber, no electric field. But there's electric fields around the transmitter, around the repeater, they're very, very weak. But it turns out that sharks can detect electric fields, and when they find them, they like to bite them. So here's something you didn't learn in engineering school. If you're going to put electronics at the bottom of the ocean, you got to put a cage around it. But I digress. So there's disadvantages to running electricity underneath the ocean, is my point there. So you can harness the energy of the waves as they hit the shore instead of putting bobbers out in the ocean. And that will generate electricity on land, and then you don't have any submarine installations. So here's Faraday style. So here's one where you've got a magnet moving inside a coil. Ooh, let's see if this will work. Oh, it didn't. Previous. Wow. Well, when this works, when the magnet goes in, when the magnet is moving, current is generated. So the magnet goes in, it generates current, and the magnet stops at the other side, the current stops. Then the magnet comes back, you can generate current going the other way, and then it stops. So you get a sine wave of current. So magnet moves inside a coil, generates a current. Simplest version, just attach a magnet to a bobber, a float. And this has been demonstrated on a small scale. So here's an example of one. And when scaled up, it could deliver 5 megawatts, so we'll believe it when we see it. But that's one simple version. Just have a magnet that's attached to a bobber. This one, I don't know how to pronounce this. It's named after a Greek sea goddess whose name is spelled K-E-T-O. But of course, it's really Greek, so I don't know what it should be. But this one, the floats, they move back and forth. Instead of going up and down, they move back and forth. And as they do that, there's a mechanism down here that pumps water. So there's no electricity out here. Pumps water to shore, runs a turbine over here, and that generates electricity. Same moving water drives a turbine. Same mechanism is used to drive desalination pumps in Australia. No electricity is involved. The water is desalinated by reverse osmosis. So these things pump water. They go up to land, get forced through a membrane, and desalination with no electricity, I think, is pretty cool. Here's another pumping one. This one, oh, wait a sec. No. This one, this guy moves back and forth like this. Let me see if I can pull up this video. Please. Oh, go away. It was supposed to be embedded. Well, we'll see if we can make this go. It's worked every other time. This one has no sound. I don't think. That's what it looks like from shore. So you'll have people who say that's an eyesore.
What amount of energy is something like that actually producing?
I hope I have that on my slide when we get back to it. You'll notice whenever it sprays water up, that's energy that's being wasted, mechanical energy that's being wasted. Looks like pretty rough sea there. It's also a little hard to figure out quite how big that is. Is that a bird sitting on top of it? That'd be dumb. No, some kind of sky rats. This one's clearly just a single one, so it must be a prototype. Okay, we've had our fun there. Let me just scroll down here. Oyster wave power developed by Aquamarine Power, blah, blah, blah. Hello. So this one pumps water to shore. I don't have how much power it produces. Drives an onshore turbine. See hydraulic stuff in there. This one's called the Pelamis. So this one looks like a sea snake. It's got 4 sections, floating cylinders, and the wave motion makes the sections move. So they're bobbing up and down like that. In the joints here, there are pistons that go in and out. And so that drives a generator. So the generator in this one is actually, I believe, in the snake. And then there's cables that go to the ground and go out. Electricity goes to the seafloor and is transported to... Oops. What? I bet you this isn't going to work either. No, that would be helpful. Does this make it full screen? No.
Bottom right hand corner of the video.
Here?
No, of the video itself.
Oh, here?
Yep.
Crazy. So I don't know how well you can see these pistons that are going in and out. Oh, well, okay, fine. It's going to show us. Electricity carried to shore.
Question.
Yeah.
Why don't they carry the electricity like on the top of the water and put the cable on top of the water?
Probably because boats would go across it, and
Oh, no, true.
just a guess.
How would these devices work in like storms, tropical storms and stuff?
That's a very good question. How reliable would that thing be if the waves got
Like,
really...
to be ripped off.
Or if they have like a locking mechanism on it or something.
I'm not sure. So the comment was maybe there's a locking mechanism, but I'm not sure that would help. Maybe it would just make it a big, rigid thing to get destroyed. The other thing is they must have to tailor this to the location because I was doing some calculations on wave power, and the answer depends on the frequency of the waves, the time period of the waves, which depends on where you are. So that would determine the wavelength of the waves. Well, maybe it doesn't matter. It seems like to get maximum efficiency, you would need to have that thing flexing at just the right intervals, but maybe that's not right. More videos for your viewing pleasure. Oh, escape. I remember now. They said, here's how you get out of this. What does it take to make the wave machine? So there's energy that goes into building it. It has about 350 tons of steel. That has to be manufactured. It weighs about 700 tons. It creates 750 kilowatts, to answer that question. So the weight to power ratio is about 500 kilograms per kilowatts peak, compared to an offshore wind turbine, which weighs 500 tons and puts out 3 megawatts. Its weight to power ratio is 170 kilograms per kilowatt. So this looks like it's more weight to power. And the other thing, remember the offshore wind turbines for Denmark? They all had to be replaced because of the salt environment. So these guys have the generator motor inside the unit, so I don't know how hard that is to keep it away from the environment. Here's an onshore type of wave energy capturing device. Here the waves hit the shore and they rise and fall in this chamber. As they go into this chamber, the water flows in, it squishes this air, compresses it, and pushes that thing over there, the pressure goes and drives a turbine. Here's the picture here. So people say it's very noisy because you have all this rushing air going in and driving a turbine. On the other hand, waves are noisy too. So any one of these things, there's going to be somebody who says, well, I don't like the look of it, I don't like the sound of it. This one back here has the advantage, according to the manufacturer, that it's all beneath the surface, so you don't ever see it. So all you have to hope is you don't have any submarine traffic. Here's one, wind and waves combined. So they have a floating platform that uses hydraulics to collect energy from the waves, and they put windmills on top. I'm thinking, and why not put solar cells under there too? So this is a Danish proposal. It hasn't actually been done. Well, there's a picture here, but I don't think it's been done on any real scale. But I think that's smart. If you're going to be out there building stuff, why not? So here's your waves. Here's the wave energy, 40 kilowatts per meter of coastline. In the UK down here, it's 250 kilowatts per, should be kilowatts per meter. Oh no, I'm sorry. Here he's saying it's a 250 kilometer long shoreline. Here's a 750 kilometer shoreline in that general direction. So two main ideas is you have the length of the coast facing the open ocean, so you have watts per meter of coast, and then the efficiency of conversion. So we can use these ideas when we figure it out for Ohio. Here again is the potential for the UK. They got very strong waves up here, less down here. And I can't read these numbers. I can't read them, so I can't tell you what they say. So he calculates the potential. He says 40 kilowatts per meter. He acknowledges that may be optimistic. But if you have 100 or 1,000 kilometers of shoreline, you have the 750 and the 250, divided by the number of people times the energy or the power per meter times hours per day, meters per kilometer. 50% efficiency, if you want to believe that. And he's saying, suppose you use half of the coast of England, that would still produce 4 kilowatt hours per day. Yeah.
Right?
Huh?
Per person.
Per person. Yes. You can see the per person part down here. But good, thank you for making me say that. So putting it on a stack, where's the stack? So it's starting to look pretty good for England. Deep offshore wind, shallow offshore wind, and then the waves. It's a little bit, but it's adding up there. The assumptions are, would you say pretty optimistic? Would you say wildly optimistic? Most people are saying yes. All right, so now let's look at the next type of energy consumption, which would be food. First, though, evidently we have another picture of global wave power. And the U.S., we look good in California. We're not so good on this coast. We don't get to use any of this, but it's not that great. This is blue, purple is weaker, and red is higher. Here's a good place to be. I don't know what's down there. Is there something there? I don't know. I don't think there is anything down there. Evidently we have more wave power here. So compared to the UK, we have 5 times the population. We have 5 times the coastline if you throw in Hawaii. About the same intensity of waves. Check my work. Green to aqua. Green to aqua. So we might get about the same 4 kilowatt hours per day per person. Would we really build out half the coastline? California? No, I think maybe, well, I guess it would depend. There's certainly nothing where you're collecting the wave power on shore. Certainly it's not going to be those ones where the waves rush in and compress the air and drive a turbine. Maybe if you had those submerged guys out in the ocean, maybe people would tolerate that. Of course, we have a lot of shipping on the West Coast. And then you also have the problem with waves are violent, and who's asking about what happens in a storm? I think, Destiny, that was you, wasn't it? Yeah. So we got to do this for Ohio. So I found out, Ohio, here's Lake Erie, here's Cleveland, and here somebody did some measurements. And actually, it turns out the guy who did these measurements is a professor in civil engineering right here. And so these buoys, he measured the wave height in meters and off of Cleveland. So this is our part of the lake, like here, you know, Pennsylvania gets that part, Canada gets that part. And we actually have the better, oh no, sorry, his plot is upside down, so red is low, which is not the usual way. So we have the sucky part of Lake Erie. And this buoy right here is in light green, that's about 1.5 meter height waves. So calculating potential in Ohio, I said the estimated wave height in our part of the lake, we'll say 1.5, that was the peak, but we'll just say that's what it is. And then he used a deep water formula. Why? Because that's the one I could find. But Lake Erie isn't deep. So is it deep enough? It's kind of on the edge. So we'll just look at this number to kind of get a idea, but we're not going to put too much stock in it. So you have all these things, a bunch of constants here, but it works out to a 0.5 kilowatts per cubic meter times second times the height squared of the waves, and this is the time period of the waves. So we got the height, now we need the time period. I'm thinking there's no way I can find data for that, but it turns out, I'm an awesome human, gotta love the internet, I did. Same guy, Alper Yilmaz over in civil engineering. And that's a plot of the wave periods. So I said if typical wave periods, the scale here, this says 4, this color, 6 is that dark color. I said for our part of the lake, maybe 4 seconds. So I worked it out, and I got 4 kilowatt hours per meter of coastline. What did McKay use? 40, right here. Well, that's to be expected. He's got an ocean. We got a pathetic lake. Our lake is good for wind, though. Make no mistake. I didn't mean to say it was pathetic. So I'm going to let you finish the estimate for Ohio for homework. I have to remember to put that in your next homework for your viewing pleasure, or on a midterm or something. All right, now we get to talk about food. How much is the typical U.S. caloric intake in kilowatt hours per day? Here's your choices: 0.1, 0.3, 1, 3, 10. This is where I'm supposed to have clickers, but I can't afford them. So how many people think it's 0.1? Okay, we have 1. How many people think it's 0.3? Nobody. How many people think it's 1 kilowatt hour per day that we eat? How many people think it's 3? We have a couple. How many people think we eat 10 kilowatt hours per day worth of food? Pop-Tarts, my favorite. Turns out it was 3. Here's caloric intake. So here's some scary numbers. Men, this is 1971, here's 2004. 2450, 2618. Women, 1542, 1877. It's been going up. Average 2000, 2250. So if I take the 2300, I'm using this number and I'm figuring it went up since 2004, converted all the units, blah, blah, blah. I came up with 2.7 kilowatt hours per day per person that we eat on average. And so that's close to the 3 that I had highlighted on the last page. You convert this to food. So you eat the food, and then you take the atoms and you convert them into hair, skin, guts, sweat, poop, etc. I used to tell, I had a friend who had a dog, and I told him his dog was made out of Alpo, which is true. So then you convert the energy, so you convert the atoms into these things, you convert the energy into food, use it to run your metabolism, and maybe you generate some heat. So what's the energy cost of producing the food that you eat? Something's missing here. So I'm going to take a break here for a second and show you a fun experiment. Oh, be bigger. Is this bigger? Will this make it bigger? Yeah. You can't hear that, but this is me burning a Cheeto over my grill outside. The grill is off. I got a Cheeto on a piece of wire, and I'm setting fire to it. The question is, how much energy is in this Cheeto? So let's see how long it takes to burn. I expected this to just flash. How many of these did you eat during the Super Bowl? says 160 calories per serving, 10 grams of fat. This is one Cheeto. Now, that number wasn't, but this is one Cheeto burning. That was one serving.
That's taken a while.
Isn't that amazing? That's a lot of flame. You could eat a romantic candlelight dinner by this Cheeto. My sister's a biochemist. She does this for her class every year. But she has stuff, you know, beakers and things to protect, and I didn't. I wanted to do it in here, so I was afraid I'd stink up the conference room. So that's why I recorded it. Still burning. It just went out. But we can see there's more there. It's hot.
Now we know what to use for fire starters.
Yeah, there you go, Cheetos. There was certainly, oh no, that was Doritos there were commercials for yesterday, weren't there? All right. Oh, this is where I was supposed to say don't try this at home, but go ahead. All right, now, where were we? All right. I thought I'd put that in here. I must not have put the latest copy on my stick. All right, so how about a nice glass of milk? So a cow produces 17 liters of milk per day. If you drink a pint, as McKay says, you're employing 1/32 of a cow. The cow consumes about 21 kilowatt hours per day. So the cost of your milk and energy is about 0.6 kilowatt hours per day. I should say kilowatt hours per day. And if you also eat cheese, maybe call it 1.5, depends on how much cheese you eat. So there's energy in the energy cost in making the food that we eat. How about eggs? Chicken eats 110 grams of chicken chow, of which about 3.3 kilowatts per kilogram is metabolized. The chicken consumes about 0.4 kilowatt hours per day. Maybe it lays, I guess it's a she, 290 eggs a year, so the average energy cost of eating 2 eggs is maybe a kilowatt hour. For eating 2 eggs? Give me a break. Energy constant is 160 calories. Egg production is therefore about 20% efficient. Okay, milk and eggs, you're just renting the cow or the chicken. The old saw is the chicken's involved and the pig is committed. You heard that joke. Average meat consumption by Americans, half a pound a day, so about 227 grams. Average American eats 195 pounds of meat a year. That's what you eat, doesn't include the bones and stuff that you put down the garbage disposal. Chicken is about 50 days from hatch to hatchet. I just like that expression. Chicken eats all that time, so it's consuming energy. The pig lives about 400 days. The cow lives about 1,000 days. Feeding these animals takes about 12 kilowatt hours per day to supply food for 1 American. Average American eats 2,500 to 3,700 calories a day. Say 3/4 of it comes from meat and dairy, as the book assumes. I don't know if that's true anymore, but it probably was a few years ago. So call it 2,000 calories or 2.3 kilowatt hours per day. So that's an efficiency of about 20%. Animals converting plants or whatever they feed them, which isn't always plants, to meat. Cost of raising animals per meat, 8 kilowatt hours per day per person. Wow. I'm going to eat plants, all right? But I still expect someone to grow those plants for me. So they're going to use fertilizer, maybe 2 kilowatt hours per day per person. They're going to use farm machinery to harvest that and plow it and plant it. And they're going to refrigerate maybe, so maybe another 0.9 kilowatt hours per day per person. And oh, that doesn't include somebody driving the food, the plants, to the grocery store so I can get it. More growing plants. One estimate says that 10% of all energy used in the U.S. goes to food production and distribution. I'm guessing it's this estimate. Research at Johns Hopkins says it takes 3 calories of energy to produce 1 calorie food on the average. So grain-fed beef takes 35 calories per calorie. So it takes 35 calories per calorie to make this kind of beef, this kind of food. And this doesn't include processing or transporting. So you can change your impact or your energy consumption by choosing what you eat. So let's emphasize this. If you eat a plant, you got the fertilizer, the farming, the processing, and the transportation. If you eat an egg, you eat all the stuff to grow the stuff that the chicken eats, plus 20% of the energy that feeds the chicken appears in the final product, the egg. Or you're going to cook that egg. That takes energy. Chicken care, processing, packaging, and transportation. Did I dream this, or is there a new diet out there where people eat only raw food? Did I dream that? I read about the paleo one where you only eat things a caveman could eat. I don't know if that means they eat their food raw or not. Big energy cost is in fuel for the tractors, combines, and trucks, right? Actually, no. 40% of the system used in the food system goes to making the fertilizers and pesticides. So there's a reason, I guess, to eat organic, although that doesn't get rid of the fertilizers. You could use manure as fertilizer. That's good if your manure factory is near your plant factory, so that you don't have to move manure around, so it's costly to transport. So you want to use it close to where it's produced, if you catch my drift. Distribution costs are not insignificant. So average American foodstuff travels 1,500 miles before you eat it. I like to have fresh vegetables in the winter, so they're coming from Chile and Australia and places with better climates, or diametrically opposed climates, I guess. So now a lot of people are pushing to eat more local food, and this is one of the reasons. All right, I'm going to grow my own vegetables, which will be great in the summer. So if I plant the green beans in May, I'll start getting them in August, and I can eat them August, September, October, and pretty much I'm done. So I'm going to have to get a real big yard to keep me alive for a year. I want somebody else to have the yard, but then I want the yard to be near me so they don't have to transport the food. So here's some different kinds of diets. A vegan diet maybe consumes 6 to 9 kilowatt hours per day. They got 3 kilowatt hours from food, 3 from farming, and 0 to 3 from waste. Vegetarian, 9 to 12. It's everything the vegan has, plus they're allowed to eat dairy and eggs, so throw another 3 kilowatt hours on their stack. Omnivores, depends how much meat you eat, but vegetarian plus maybe 8 kilowatt hours for meat and some more for waste and storage. It's a real eye-opener for me. All right, here's the stack. Food, farming, and fertilizer, 15 kilowatt hours per day. So England's looking pretty good over here. Oh, and I can eat plants, but my dog Kelsey cannot. Here's Kelsey. Big, ferocious German Shepherd. And here's a cute little kitty. And then I used to have fish. I love fish. They're so beautiful to watch, but of course I had to run the pump and the light and feed them fish food. Purina Fish Chow. 9 kilowatt hours per doggy. 2 kilowatt hours per kitty. I don't know what the fish are. And food. Here's the text energy interface. So here's the plant. Maybe you take the plant and you eat the plant. Or maybe you take the plant and you process it, transport it, and then I buy it. Or maybe you take the plant and you feed the animal, which then gets processed, transported, and all that. Here you have the supermarket, restaurant, storing, cooking and waste, factory, preparation waste, cooking and freezing, farm, they gotta heat those, barns, they gotta light those, incubators, they gotta heat those, farm, tractor, fertilizer, greenhouse. Maybe I should do that paleo thing. Maybe I should just go live in a cave. I don't want to live in a cave. So this is the same stack we saw a second ago. What about telecommunications? So I found something somewhere that said that telecom is about 4% of the U.S. economy and uses about 4% of the energy. I was surprised it was that high. And question is that a good thing or is it a bad thing? Can we improve the world by reducing our telecommunications or increasing? What do you think? This Monday, everyone's too shy. Well, online shopping, So I'm not driving to the store, but somebody, the FedEx guy, is bringing me the stuff. Teleconferencing. Now I'm going to meet with somebody in Milwaukee. I don't have to fly there, so that's a plus. I think I save more energy by just talking digitally. Working from home. If I work from home, I don't have to commute. But on the other hand, if I work from home, I'm going to eat more of those Cheetos. Fun fact. So some people here are engineers, but for those of you who are not, you can tell what an antenna's for, more or less, from its shape. So radio frequency beams expand fastest from the smallest emitting aperture. So if you take a cell phone tower, the cell phone antenna is long and skinny. The aperture is small this way, so the beam spreads out a lot horizontally. But it's taller this way, so the beam doesn't spread out as much vertically. So this shape of antenna produces a beam that's flat and covers the earth, which is exactly what you want. So to design and cover the ground. Now, if you take these round guys that are on the tower too, these are circular. Their beams don't expand more in one direction than the other. They're aimed at another tower. So they're sending signals back and forth from one tower to the next. This guy also has cell phone antennas on it. Just a fun fact, when you're driving around, don't look at these things when you're driving around, you crash. Here's some more telecommunications numbers for the U.S. AM radio, total power, gigawatts, let's look at kilowatt hours per day. Negligible. AM radio transmitters. FM radio transmitters, 10 times as much, still pretty small. TV transmitters, 10 times as much as that. Cellular, this stands for base station. Don't get any bad ideas. 0.2, cable TV, 0.1, internet, who knows? Data centers, Google data center might be a kilowatt hour per day per person. It's interesting. So to summarize where we are so far, wave energy, unlikely to be more than a few kilowatt hours per day. And the environmental cost, the person who put too high in here was the person who prepared these slides from Colorado. It's up to you to decide if it's too high. Food, a vegan is 3 times more efficient than an omnivore. Eating locally produced food makes sense from an energy point of view, as long as you don't want fresh vegetables in January. Here's a question about oil. The U.S. uses 20 million barrels per day. How many kilowatt hours per day per person do we think that is? Who knows? I don't have my calculator handy, so I'm going to go straight to the answer. Oh! Wow. 20 million barrels per day. How many kilowatt hours per day per person? 100 kilowatt hours per day? That's enormous. Oil is, barrel is 42 gallons and 20 megabarrels per day, 160 liters per barrel, 1 over mega people, this is people. Kilowatt hours per liter is the energy density of fuel. Whoa. This is a quarter of the world's daily supply. Also results in a quarter of the world's CO2 emission. Well, here I've been worried about electricity all this time. Look at all this oil we're burning. What do we use it for? Supply sources, percent of source, demand sectors, percent of sector. Petroleum, 37.1% of this is our supplies. This 71% of it goes to transportation. Shipping the groceries to my store. 23% industrial, a little bit, 5 residential, commercial, 1 for electric power, not much. Demand sectors, 27.8% transportation. Percent of sector, petroleum, natural gas, renewable energy. I don't know what that means. Natural gas, only 3% used for transportation, 34 for industrial, 34 residential, commercial, that's my gas oven, 29% for electric power. We do burn some natural gas. Coal, 91% electric power, 8% industrial, of course, you're not used for transportation anymore. Less than 1% residential commercial. Renewable energy, 7.3. This data is from 2009. 11% transportation, 28 industrial, 10% residential, 51% of this is electric power. And nuclear energy, 8.5%, all used for electric power. We don't use petroleum to generate electricity. Oil's not, what?
Would the nuclear also be for like, what about the nuclear submarines? Count that under transportation.
We're gonna put that under defense. Actually, when we do defense, I believe that's where it is. I don't think there's enough submarines to make it significant, though. Oil's not renewable. So the renewable energy source that we've looked at mainly is for electricity. Some produce heat. To use electricity for transport, we need electric vehicles. So let's put that aside and go on to our next renewable energy source, tides, which I think we should do next class because the time is almost up here. Are there any questions? Go home and burn up some Cheetos. All right. Run and play.
Yeah, I checked the Carmen again.
Yeah?
We don't have access to the attempts that we make on the quizzes. So
I'll see if I can figure out how to fix that. Did I make changes? I didn't make changes.